Good afternoon, everyone. I'm really excited to be here and to talk about some of the advanced AI research that we are doing at Oak Ridge National Lab within the AI initiative, which I lead. The AI initiative is focused on secure, trustworthy, and energy-efficient AI for scientific discovery, experimental facilities, and national security. I will be primarily focusing on scientific discovery and touch upon some aspects of AI security at the end. Oak Ridge has a very rich history in leveraging AI for science. The first AI project started in 1979. It is called Applied AI Project. And this is a review article in 1981 that came out of Oak Ridge, where there were projects, AI projects, that support spectroscopy, environmental management, nuclear fuel reprocessing, and programming assistance, the expert systems that can sort of write Fortran code, right? So now, today, we have GitHub Copilot and Cursor and other kinds of things, but it's really fascinating to look back at the history and say, like, how people thought about developing such kind of system to advance science and scientific discovery. And then during the AI winter, the focus was primarily on robotics, so automated machines to monitor environments, and there is also a lot of robotic studies, developing systems that can play chess and other kinds of things. And then there is something interesting happened. In 2017, we had Summit. It's a supercomputer that was made of CPUs and GPUs. At the time, it's a heterogeneous platform, right? Although the machine came in 2017, the decision to go to GPU happened back in 2012 because it always takes 5 years in DOE complex to build systems. At that time, CPU was already hitting the limit, and people in DOE, especially in Oak Ridge, said, like, hey, look at this gaming company called NVIDIA, who is developing these graphical processing units for essentially for gaming, right? Can we take that and accelerate scientific computing? It's, if you think about it, it's a huge risk that DOE, and specifically Oak Ridge, made at that time. So, hey, OK, let's go and bring the gaming hardware for accelerating scientific computing. But essentially, they made it, right? The decision for NVIDIA, so they helped NVIDIA to co-design the system and to build this supercomputer and showed that it is possible to accelerate scientific computing through graphical processing units. And then today, we have Frontier. It's the second fastest supercomputer on the planet for open science. First supercomputer to exceed exaflops, and in mixed precision, it can already do 10 exaflops, which is great for AI. In fact, we are leveraging those capabilities to train large AI models for science. In fact, we trained models up to 1 trillion parameters on Frontier 1 year ago. AI is fundamentally transforming the way that we do science at Oak Ridge and across the DOE complex. So here are some examples. Spallation Neutron Source is a user facility where we use AI to process data at the facility so that we can give near real-time insights into the experiments. And all the way up to high-flux isotope reactor, where we increase the production of isotopes using AI. One thing I want to point out is Oak Ridge Leadership Computing Facility, where we are using AI to accelerate modeling and simulation, like very, very expensive simulation codes. So I will talk about it in the rest of the talk, but just a high-level idea of like where things are going within the DOE complex with respect to AI for science. Great. Despite all these promises, the promise of AI is, in fact, challenged by 3 major things. So the first one is lack of physics understanding. Right? So we can build essentially large models. Even if you take large language models, right? It can give you text. It can give you images. It can interact with you. It can answer. Great. But if you really ask this question, is the model really understanding what it is doing? That's a billion-dollar question, right? And when you try to take that and extrapolate that to science, that's even more profound, right? So do these models, when we build scientific machine learning models and large AI models, do they really understand the computational fluid dynamics? Do they really understand the biology? Do they understand the fusion process, and so on and so forth, right? The lack of physics is a big challenge for us. The second thing is trustworthiness. Especially in science, it's not about building a model with very high accuracy, because we know these models will work for certain class of inputs, and it will not work for other, right? So there is no way that a model will work on all different types of inputs, right? So the trustworthiness of the model becomes a crucial talking point when it comes for deploying these models and using these models to advance science. And several people already talked about the cost and energy efficiency, right? So it is estimated that in 2030, 10% of US energy production will go to large AI data centers, right? And that's a huge, huge cost. We have a moral and ethical responsibility to address this energy efficiency issue. Is it easy to address all these problems? In fact, no. AI development has paradoxes, right? So first and foremost, when it comes to AI, it's easy to demo, but it's very, very hard to put into production. Right? So today, you can easily go with all the software stack and GitHub Copilot and Cursor. You can easily write a model in a Jupyter notebook and say, hey, it's predicting well. It's great. But when you try to put into production, all the things will break. Hard problems are easy, and easy problems are hard. Right? So today, we are at the point of civilization where we can take everything that is known to mankind and synthesize into one model and query the model, get answers. But we cannot build a robot that can wash dishes reliably, right? Things that are so easy for us, it's very, very hard for AI to do, whereas things that are very, very hard for us, easy for AI to do today, right? They're ever-growing open research problems. So not long ago, like 6-7 years ago, as an AI researcher, my focus was like how to make the model to reliably predict cat and dogs, right? That was a question, right? So that was a big challenge. We were not talking about hallucination. We are not talking about AI taking over the world. We are not talking about AI security and vulnerability and so on and so forth. The more complex AI model that we build, we are facing completely different set of questions and challenges, right? If you think about it, the more complex and more sophisticated approach that you develop, it should solve problems, right? But AI is a little bit paradox. It's opening up new set of problems to deal with. Humans remain a roadblock because it is important to validate and verify. There is no way that we can get into a billion parameter model and understand what the model is doing. This is one of the big challenge, right? So unlike software, right? So million lines of code, we know how to write unit tests, coverages, and other things to properly validate and verify a software code. Whereas AI models, although considered as a sort of a software artifact, it's very, very hard to validate and verify. There are various unique challenges associated with cyber-physical systems, right? So there's one thing about interacting with ChatGPT. There's a completely another ballgame when you take a model and ask the model to drive a car, and you know what happens, right? So we are looking at various types of challenges, and the AI initiative that I lead in the lab focuses on two axes. So the first one is application axis, is AI for scientific discovery in complex systems, AI for experimental facilities, and AI for national security. And on the foundation axis, we focus on developing algorithms, foundational algorithms to advance security, trustworthiness, and energy efficiency. Within security, we have alignment, cybersecurity, robustness, and trustworthiness. We focus on validation, verification, uncertainty quantification, and causal reasoning. And energy efficiency, yes, we have the largest machine at our disposal, but we prioritize energy efficiency as a sort of first-class citizen when training large models. We also look into edge and novel AI hardware. One thing that we are very, very excited about when it comes for AI for science is the concept of foundation models, right? So the foundation models are similar to large language models, right? So you take a large amount of internet text, and all you do in the pre-training is predict next word, right? And then you take that model and fine-tune that for reasoning, for game playing, text generation, poem generation, and whatnot, right? So there are various ways to fine-tune that model. We are taking a similar approach for science. Here, think about this, right? So we have large amount of simulation data, spatiotemporal simulation data, combustion, computational fluid dynamics, and so on and so forth. Want to take all the data and train a large model, or pre-train a large model on Frontier, right? So it's a multi-scale foundation model that knows different scales, different dynamics, different physics, and so on and so forth. Then take that model and fine-tune that and adapt that for various types of downstream applications. And this downstream application includes modeling and prediction, feature extraction, control, design optimization, and system identification. Okay, towards that, the first and foremost thing that we need is to have this large model training capability. And what we have at our disposal is Frontier. Frontier is not designed, the exascale machine is not designed with AI in mind, because the design decisions were all made pre-dinosaur era in terms of AI, right? So it's 5 years ago. So, which means this system is designed primarily for modeling and simulation. And the first thing that we did is like, how can we train large AI models on Frontier, where the interconnect is not as fast as our state-of-the-art NVIDIA interconnect. So we have to really think about redesigning the training with respect to slow interconnect. So we need to minimize the communication as much as possible. So when it comes for training large models, it boils down to trading off computation with communication, especially if we have to look at the models. Large models, it's like tensor parallelism, pipeline parallelism, model parallelism, and data parallelism. Different types of parallelisms and different choices one need to make. So we sort of like, what we did is, roll up the sleeves and do what HPC community usually do. Look at the kernel, how to improve the performance. Look at the communication, how to improve the performance. Okay, we know we have the slow interconnect, so reduce the communication as much as possible. We have large number of GPUs, so do more compute, do a lot more data parallelism. So we have to sort of rebalance the compute and communication patterns and trained very large model, trillion parameter language model on just 8% of Frontier. It's not just about the model size, it's also about the efficiency. So we got more than 80% of efficiency by doing this first principle system engineering, co-design, model co-design and performance optimization on this machine. And more importantly, now we also sort of democratize this recipe for everyone to use. So if anyone wants to train large model, he can go to Frontier and just call the software stack and call this module and train models, right? Previously, it is a sort of a recipe that is only available for big players in their cloud, in their big machines. But now we are enabling anyone who can get into this machine to train such kind of large model. So language model is something that industry will solve, right? So it's a problem that industry will solve. But there are several problems that industry will not solve, which are very specific to scientific computing and scientific machine learning. So one of them is graph foundation models for material science. So if you think about material science data, these are not language data, right? So these are material structures, and we want to sort of learn material structure and correlate that to the properties. So we want to go from material structure to property prediction. So to that end, what we did is, we have large amount of open source material data, 5 terabytes of data. So we took that and sort of, the distribution of the material that we have sort of shown in this periodic table, and then developed a large-scale graph foundation models. These models are different from large language models, right? So these are graph foundation models. The input is graph, and we had to we had to architect a different type of training for this large-scale graph foundation models. And we scaled this up on both Perlmutter and Frontier up to 16K GPUs on Frontier and Perlmutter 2K GPUs, and again, doing all the things that we usually do in HPC, do performance optimization and get good scaling. What this enables? This enables something like this, right? So in material science, often the question is, You have billions of different candidates, and you want to find a handful of promising candidates so that you can go and do much more detailed simulation, right? Because simulating each one of them is very, very expensive, right? DFT or quantum Monte Carlo, it's a very, very expensive simulation. AI is a sort of a filter that will quickly identify promising candidates, and we can take it from there. So here are some examples. The chromophore design, so what you see there, I don't know if you can see the pointer. OK, but each dot there is a representative candidate, and there are millions of them. And the ones that are enlarged are the most promising chromophore candidates. We went from millions to these promising ones within few minutes, thanks to the foundation model that we trained on the large material data, which is then fine-tuned on chromophore data, which is then used to sort of filter out large number of candidates and identifying the promising ones. The other one is a generative model that sort of generates high entropy alloys, which has applications in various types of aerospace and manufacturing applications. We also did something similar for climate models. So this is a spatiotemporal model. Think about the complexity. Language is one-dimensional sequence. It's a very large sequence, but it's 1D. But if you go to CFD, it's a spatiotemporal. Each point in the space is a sequence. Now you have millions of grid points and time series for each of those grid points, right? So that's what the climate data is about. So we trained a very large spatiotemporal foundation model on CMIP6 simulation data, and then took that and fine-tuned that on various types of tasks, right? So weather climate prediction and yearly prediction, week prediction, and so on and so forth. We scaled this on Frontier on 49K GPUs and achieved 70% scaling efficiency. And this was a Gordon Bell finalist for climate modeling last year in 2024. Orbit achieves, thanks to the foundation model, right? So if we can build those kind of models, it can provide prediction in milliseconds, right? So compared to traditional modeling and simulation for climate, which takes hours on big machines, right? We can take the data, develop a surrogate model for that, and then once you have the fine-tuned model, you can run that on your own laptop and get predictions within few seconds. That is transformative. We extended that to computational fluid dynamics, right? So we have large amount of computational fluid dynamics data that spans aerodynamic simulation, fusion energy, urban wind. So there is sort of this underlying computational fluid dynamics phenomena that crosses many different things, right? So we take all this data and pre-train a model, a large model, across all this data, and then fine-tune that for specific applications. Again, we are getting really good results with such kind of foundation model on magnetohydrodynamics simulation, sort of trajectory projection, and so on and so forth. So these are all the sort of the foundation model side, but we are also developing the trustworthy stack for the foundation model. And the trustworthy stack here, we are focusing on uncertainty quantification, so where we develop models that not only give predictions, but also uncertainty bounds, uncertainty estimates for those predictions. Explainability to sort of ensure the physical consistency, because if we can explain what the model is doing, then we can map that with our physical understanding to say, yes, the model is physically consistent. We are also doing validation and verification. So this is very domain-specific, various ways to validate and verify these models, both in an automated way or a semi-automated way, which is very, very important, right? So we have to make sure that we are implementing the model right, and the model is reflecting the physics in the correct way. Some examples of uncertainty quantification. So we developed this uncertainty quantification library and applying it to various types of problems. Uncertainty is, on the one hand, it is about establishing trustworthiness, right? We want to establish trustworthiness, but also plays a major role in design of experiments. So that's the example where we use uncertainty to drive what are the next set of experiments that we have to do. So for example, if you have a model that is trained with uncertainty, we can look at the uncertainty and say, like, wherever the uncertainty is larger, that's the place where the model is not confident, so where we need to gather more data, right? And that allows us to do much more targeted experiments as opposed to experiments that span a wide range of areas in neutron diffraction characterization. Causal modeling is a next frontier. Yes, we do a lot of predictive modeling, but often scientists are interested in causation, not correlation, right? So predictive models are really good at capturing correlations. So causal models are one in which we say, what is causing what? So to begin with, we sort of start with Bayesian formulation to sort of say, what is a prior? Like, what do we know? And this information can come from large language models or knowledge graphs that says, OK, this is causing this one in this particular material setting, right? We start with that. And then we run experiments to update that Bayesian graphical models to improve and to increase the accuracy of causality. This is very, very hard thing to do. It is very hard to generalize as well. But wherever we could get success, it's very, very transformative. This is another example where we connect large experiments with big supercomputers. So this is an example from spallation neutron source at Oak Ridge, which is a big experimental facility that do material characterization. But while, if you do characterization with that, it produces large amount of data. And what you have to do is to process that data and provide insights near real time so that you can, in this specific example, you don't have to overrun the experiment. You can terminate the experiment much early. And in this particular case, what we did is move the data from spallation neutron source to Oak Ridge Leadership Computing Facility at Frontier. We trained the model, very large-scale model because the data is very large, and then use that model to say, OK, I can predict the next step in the experiment very well, or I cannot. So as long as I cannot, then I keep on running the experiment there in the spallation neutron source. And as soon as my accuracy gets better, stop the experiment. So it was very, very, very interesting work, very impactful work to sort of connect this large-scale experimental facility with high-performance computing, big supercomputers. It's not always about large supercomputers, but we also do tiny AI, right? So this is AI at the edge, where we have this real-time segmentation that we have to do on this device. And what you see here is the image and how to do this segmentation. And here the model is sort of trained on DGX and shipped to Jetson Nano and FPGA, which is much, much closer to that instrument. And then we do inference there. So whenever there is a new distribution, new set of data, we have to move that back to DGX and retrain the model and bring it back to Jetson Nano. This is all. This particular slide is on the AI security, so which I will not go too much into detail because of lack of time. But essentially, we are asking this question, like, what are the threats emanating from AI, and what are the threats to AI that is deployed in experimental facilities or deployed across applications? So we have this center called CASER, Center for AI Security Research, where we are developing foundational algorithms to test AI model vulnerabilities. And these vulnerabilities range from hallucinations for language models all the way up to robustness testing for scientific machine learning models. The one thing that I want to stress is the vulnerability testing needs scale. Usually people do this by hand in a small sort of in a loop in a very limited setting. But bringing HPC to vulnerability testing really changes the game. We can extensively test the models on wide range of inputs across different dimensionality. And in fact, we can learn what are the vulnerabilities of the model and iterate on those vulnerabilities, like basically learn where the model is weak and poke the model in the weak area much more to understand what the model can do and cannot do. Conclusion. So we are using AI in many different forms. AI is used to discover and design new generation materials and new chemical processes. for clean energy and for energy dominance. We are using AI to advance fusion and fission science. So here it is about fission materials, surrogate modeling for fusion and fission simulations, and reactors. We are using AI to improve the isotope protection, where we use AI to sort of increase the experimental, increase the efficiency in these kind of isotope protection facilities. These isotopes are used for cancer treatment and also used in remote operations in different planets like Mars. We use AI to improve national security. So this is the one thing that I talked about is AI vulnerability and AI testing, but there is also a rich portfolio of cybersecurity in the lab where we use AI to improve cybersecurity. We use AI to model climate and biological processes and use them to understand various types of mechanisms that governs these processes. Finally, I want to end with this slide. So there were conversations about, is AI going to replace HPC? Or HPC is going to stay, and AI is going to play an intermediate role. I think there are a lot of interesting examples that are coming out. But all of them point out to one thing. It's not AI or HPC. It's AI and HPC. It's the synergy. AI is accelerating what we can do with HPC. And HPC is accelerating what we can do with AI. So I feel AI and HPC are the sides of the same coin. The synergy is going to fundamentally transform the way that we do science and to advance scientific discovery. Thanks for the opportunity. Happy to take some questions.